Welcome to a story of innovation, secrecy, and technological superiority that reshaped the skies of World War II. In early 1944, over Dayton, Ohio, a daring experiment pushed a P-51 Mustang beyond its known limits, fueled by a revolutionary grade of aviation gasoline that promised to change aerial combat forever. What if a single chemical breakthrough could make a fighter aircraft faster than ever before? Could a simple fuel upgrade outpace entire enemy strategies? Did the Germans truly underestimate the power of American science? How did the secret development of 150-octane fuel, dyed purple and crafted in clandestine laboratories, alter the course of the war? And what would happen when German fighters, once confident in their speed, suddenly found themselves outstripped by aircraft operating on a chemical advantage they never foresaw? This wasn't just about engines or aircraft design. It was a chemical revolution behind the scenes, an unseen weapon that gave Allied fighters the edge they desperately needed. The implications were staggering. Speeds at 25,000 feet soaring past 448 miles per hour, German fighters struggling to keep pace, and the entire aerial landscape transforming before their eyes. How could such a small change in fuel chemistry produce such enormous results? Why did the Allies' scientific teams succeed where the Germans faltered? And what secrets did the American refineries hold that the Nazis could only dream of replicating? In this video, we will trace the journey from peaceful research laboratories to the front lines, uncovering the meticulous science behind high-octane fuels, the engineering feats that unlocked new performance thresholds, and the strategic consequences of this hidden chemical war. We will connect the dots between laboratory breakthroughs, the daring flights of pilots pushing engine limits, and the decisive air battles that decided the fate of nations. Prepare to see the war from a new perspective, not just fought with guns and planes, but powered by the unseen force of chemistry, an invisible weapon that changed everything. The most astonishing part? The real story is just beginning. Let's dive into the first chapter and uncover how science and secrecy turned the tide of aerial warfare. In the early months of 1944, amid the uncertain skies over Dayton, Ohio, an intense moment of experimentation unfolded near the Flight Test Center. A skilled test pilot, with a steady hand and unwavering focus, sat behind the controls of a P-51B Mustang, a fighter aircraft renowned for its performance and agility. As he pushed the throttle beyond the customary wartime emergency power limits, a tremendous roar erupted from the aircraft's engine, signaling a dramatic increase in power. This surge was not merely a routine boost. It was a deliberate attempt to unlock unprecedented performance levels, powered by a new and revolutionary fuel. The engine's boost pressure climbed rapidly to a remarkable 75 inches of mercury, a pressure level achieved thanks to an experimental grade of aviation gasoline designated simply as grade 150. The airspeed indicator needle, which might usually hover around familiar numbers, now streaked past figures that marked the very edge of what Allied fighters had previously been capable of reaching. At an altitude of 25,000 feet, the Mustang was accelerating through an astonishing speed of approximately 448 miles per hour, a speed that surpassed all earlier records and expectations. Ground-based engineers, monitoring the telemetry and visual signals, exchanged quick glances infused with excitement and anticipation as the pilot's radio report crackled into their ears. What this pilot was experiencing was far more than a mere incremental gain. It was an entirely new era in aerial combat performance. This was a genuine revolution. Cloaked amid the vibrant purple hues of dyed aviation gasoline, a chemical breakthrough that fundamentally altered the potential of existing fighter aircraft. The implications were profound and far-reaching. This fuel's capacity to unleash superior power meant that the entire landscape of aerial warfare, especially in Europe, was on the verge of transformation. This transformation was not driven by the introduction of a completely new aircraft design or an innovative tactical maneuver. Instead, it was the result of a strategic enhancement in fuel chemistry, a seemingly small but incredibly impactful chemical advantage. This advantage was so significant that it threatened to render obsolete many of the assumptions held by German Luftwaffe strategists about the capabilities of their American adversaries. Up until that moment, the Germans believed that their fighters, alongside their existing tactics and aircraft configurations, would continue to dominate the skies in both speed and altitude. What the German Luftwaffe did not yet realize was that American and British scientists working behind the scenes in peacetime had achieved a remarkable feat capable of changing the course of the war. While the Germans struggled with their own synthetic fuel program, which produced B4 fuel with an octane rating of only 91, considered quite modest, and their best C3 grade fuel, which scarcely approached the performance of the Allies' 130 grade fuel, the Allies had made unprecedented advances. American refineries, inspired by wartime urgency, had succeeded in producing aviation gasoline with a performance number of the extraordinary level of 150, a testament to the intense scientific endeavor undertaken in secrecy. The implications of this achievement were staggering. To give some perspective, an aircraft like the P-51 Mustang operating on regular, wartime standard 130-octane fuel could reach approximately 437 miles per hour at 25,000 feet. But with the revolutionary grade 150 fuel, the same Mustang, flown by the same pilot at the same altitude, could push beyond 448 miles per hour. A speed differential that was anything but trivial. This acceleration fundamentally shifted the dynamic of aerial combat. German fighters, who had come to respect the Mustang's impressive range and high-altitude prowess, would soon face a stark new reality. The Americans had effectively rewritten the rules. In the context of 1944, the Luftwaffe's primary frontline fighters, including the formidable Messerschmitt Bf-109G, which could reach a maximum speed of about 400 miles per hour at altitude, and the Focke-Wulf Fw-190A, capable of approximately 480 miles per hour under optimal conditions, found themselves at a disadvantage once their adversaries' velocities climbed into a higher echelon. German pilots attempting to engage the Mustangs with the Church-claimed speeds of 130 grade fuel found themselves fighting on relatively even ground. But once the fuel was upgraded to the new 150 grade, these German aircraft, operating at the speeds where once they held an edge, found themselves fundamentally outpaced, at velocities unattainable with their standard fuels, regardless of pilot skill or tactical ingenuity. At its core, the story of how this extraordinary fuel advantage came into being traces back not to wartime exigencies but to the meticulous research and development undertaken during peaceful years, specifically, to the diligent work of petroleum chemists. These scientists understood that the octane rating measured how much the air-fuel mixture could be compressed within an engine before spontaneously igniting, a process called detonation. The higher the octane, the greater the compression a fuel could sustain before detonation would occur. Higher compression ratios meant the engine could extract more power from each combustion cycle, resulting in during the early years of aviation, the fuel used in aircraft engines was relatively primitive and only suited for basic training aircraft and planes designed for commercial purposes. It proved to be woefully inadequate when it came to powering high-performance military fighter aircraft engaged in combat. Recognizing this significant limitation, the British, driven by a desperate need to gain any competitive edge over the formidable Luftwaffe, Nazi Germany's Air Force, began collaborating closely with American oil companies. Their common goal was to develop a higher quality aviation fuel, specifically one with a knocking resistance rating of 100 octane. Fortunately, this advanced fuel was finally produced and became available just in time for the critical Battle of Britain, where it would prove to be a game-changer. The effects of this upgrade in fuel quality were immediately apparent and striking. Aircraft like the British Spitfire and the Hawker Hurricane, which previously operated using lower octane fuels, suddenly enjoyed a significant increase in performance. With the introduction of 100 octane fuel, these fighters could achieve velocities at altitude that were upwards of 30 to 40 miles per hour faster than before. Their climb rates also improved substantially, increasing by approximately 500 to 1,000 feet per minute. For German pilots flying the Messerschmitt and Focke-Wulf aircraft, who had previously benefited from the performance advantages provided by fuels with octane ratings of 91 to 100, this development leveled the playing field, making engagements far more balanced. The technological advancement did not stop there. The subsequent development of a fuel with a rating of 130 octane marked yet another extraordinary leap forward. This high-performance fuel, often designated as a 130 grade, gained prominence and became the cornerstone of Allied air power throughout the years 1943. Its higher performance number, 30 on rich mixture settings, meant that it could sustain higher compression ratios inside the engine cylinders without knocking. This fuel powered the prolific Merlin engines running in both the iconic Spitfires and P-51 Mustangs, as well as the Allison engines in P-38 Lightning fighters. Simultaneously, it drove the massive Pratt & Whitney R2800 radial engines in Republic P-47 Thunderbolts, one of the most formidable fighters of the war. The rapid increase in production was driven by the vision and relentless efforts of pioneering aviation fuel advocate General James Doolittle. A former aviation pioneer and military leader, Doolittle had tirelessly campaigned throughout the 1930s to convince both military authorities and private oil corporations of the critical importance of investing in the development of high-octane fuels. His advocacy paved the way for modern aviation fuel technology to flourish behind the scenes during the war years. By 1943, 17 Allied refineries across various nations were churning out high-octane aviation gasoline, utilizing the catalytic cracking process, a sophisticated refining technique perfected by Eugene Hudry, a talented engineer who migrated from France and brought advanced refining expertise. This process allowed the efficient production of the desired high-octane fuels on a massive scale. American refineries led the world in output. They were producing millions of gallons each month, enough fuel to support both the vast strategic bombing campaign against Germany and the growing fleet of fuel-efficient fighters tasked with defending those bombers. In stark contrast, German fuel production remained a significant bottleneck. The Third Reich was heavily reliant on synthetic fuel derived from coal, a process that, while technically sound, was slow, resource-intensive, and incapable of matching the rapid yields of American refineries. Even at peak capacity, German facilities could produce only a fraction of the high-octane fuel that was flowing from American plants. Most German fighters, including the formidable Bf-109 and Focke-Wulf Fw-190 models, primarily operated on B4 fuel, which was rated at close to 91 octane under lean mixture conditions. Germany's top-tier synthetic fuel, called C3, was primarily used in the Focke-Wulf Fw-190 with BMW 801 engines and in certain variants of the Messerschmitt Bf-110 and other aircraft. The C3 fuel boasted an octane rating approximately equivalent to the Allies' 1130 grade fuel, but it was available in much more limited quantities. By the year 1944, roughly two-thirds of German aviation fuel production consisted of C3 grade, yet this still only represented a small percentage of the total fuels, greatly overshadowed by the high-quality fuels produced by the Allied refineries. To fully appreciate the importance of high-octane fuel, it helps to understand a fundamental principle of internal combustion engines. Octane ratings are a measure of a fuel's resistance to detonation, or knocking. During engine operation, when a piston compresses the air-fuel mixture during the compression stroke, the temperature and pressure in the cylinder increase dramatically. If the mixture ignites spontaneously before the spark plug fires, a phenomenon called detonation, it results in an uncontrolled explosion within the cylinder. This sudden and violent event sends without causing any detonation. Traditional octane ratings are inherently capped at a maximum value of 100. This is because a rating of 100 symbolizes a fuel's resistance to knocking that is equivalent to that of pure isooctane, a standard used as the benchmark reference. When evaluating performance numbers, what is being measured is essentially how much better a particular fuel can perform compared to this isooctane standard. For example, a fuel associated with a performance figure of 150 indicates that it is capable of withstanding a 50% higher level of compression than pure isooctane without detonating. Achieving such an extraordinary level of knock resistance required specialized chemical modifications. Primarily, chemists enhanced the base gasoline with anti-knock compounds, with tetraethylene being the most notable additive used during this era. The development process involved meticulous blending, integrating aromatic hydrocarbons like toluene and xylene, both of which contributed to improving the fuel's anti-knock qualities, alongside the standard components of gasoline, carefully balancing energy content, stability, and manufacturability. During the early 1940s, British fuel chemists stationed at the Royal Aircraft Establishment dedicated significant effort to testing numerous fuel blends. Over the course of 2 years, specifically in 1942 and 1943, these scientists experimented tirelessly, seeking the optimal combination that would maximize anti-knock performance without sacrificing other essential properties such as energy density and ease of production. Their goal was to develop a fuel that could meet the increasingly demanding conditions of wartime aviation. Meanwhile, through parallel efforts, American researchers based at Wright Field conducted comparable investigations. They engaged in a productive exchange of data and findings with their British colleagues, fostering cooperation in this intense period of wartime technological advancement. By early 1943, both British and American teams had successfully produced experimental batches of what they referred to as the 150 grade fuel. It is important to note that the term 150 grade was somewhat misleading, as it implied an octane rating of 150, a figure that could not physically exist according to the chemical limits of octane behavior. Instead, this designation denoted a fuel with a performance measurement of 150 on a rich mixture scale, inside which the fuel could endure significantly higher compression ratios without knocking, while still being rated at a conventional 100-octane performance on a lean mixture scale. To facilitate their identification, these specially formulated fuels were dyed purple and underwent a battery of extensive tests during the year 1943. The results from these tests surpassed initial expectations. Engines equipped with Merlin power plants, running on the newly developed 150 grade fuel, demonstrated remarkable performance increases. For instance, engines could sustain manifold pressure levels of about 75 inches of mercury, whereas prior benchmarks with 130 grade fuel typically hovered around 67 inches. Higher manifold pressure directly translated into greater horsepower, which was a critical factor during combat operations. A prime example is the Packard Merlin V16507 engine, the powerplant that drove the iconic P-51D Mustang. When powered by the standard 130 grade fuel at designated military power settings, this engine reliably produced approximately 1,490 horsepower. However, when the same engine was fueled with the newly developed 150 grade fuel and pushed with war emergency power, as seen in the P-51B variant equipped with the V16503 Merlin, it could generate as much as 1,720 horsepower. This increase in power essentially pushed the aircraft's output to around 1,600 horsepower, substantially enhancing its combat performance. Flight tests, conducted at Wright Field, confirmed these experimental results that the performance improvements were evident across all phases of flight. Not only did the maximum speed at high altitudes increase by roughly 25 to 30 miles per hour, but the rate of climb was also significantly improving by several hundred feet per minute. What was particularly noteworthy was that these performance enhancements were achieved without any modifications to the aircraft's design or structure. The same aircraft, when flown one day on the traditional 130 grade fuel and the very next on the new 150 grade blend, exhibited a clearly measurable superiority simply due to the change in the type of fuel used. What flowed through the fuel lines made all the difference. Considering these promising results, the decision was made in early 1944 to start the operational deployment of the 150 grade fuel within frontline fighter squadrons. The timing of this decision was not accidental. It was a carefully planned response to the escalating challenges faced in the air war over Europe. The 8th Air Force, based in England and tasked with conducting strategic daylight bombing missions deep into enemy territory in Germany, was experiencing mounting losses that already stretched the limits of sustainability. Despite the arrival of the initial batches of North American P-51 Mustangs in December of 1943, the German Luftwaffe's fighters still inflicted heavy casualties on American bomber formations. The Americans needed a solution. Not only a fighter with longer range but also a machine capable of outpacing and during the intense and often perilous aerial battles of World War II, Allied fighter pilots and strategic planners understood the importance of maintaining a tactical edge by choosing whether to engage the enemy or to avoid combat when the circumstances were unfavorable. They often relied on meticulous planning and intelligence to make these decisions, understanding that fighting at a disadvantage could lead to unnecessary losses. By May of the year 1944, a significant development took place: the arrival of the first operational shipments of a specially formulated fuel designated as Grade 150 in England. This new fuel, designed to boost the performance of Allied aircraft, was distributed under strict regulation to ensure optimal use. Not every fighter group was immediately supplied with this high-performance fuel, partly because logistical arrangements required careful coordination. The robust logistical machinery of the Allied air forces, particularly the 8th Air Force, prioritized sending the new fuel to select squadrons for initial deployment. This careful approach served dual purposes: managing supply chains efficiently and conducting critical evaluations of how the fuel impacted combat performance. On the other side, the British Royal Air Force, which had pioneered much of the early testing and development of aviation fuels during the war, also began reequipping their fleet with the new fuel. Their focus initially was on units tasked with specialized missions, especially those responsible for fast intercepts against high-speed German targets. A notable example emerged in June of the same year when the RAF prioritized units hunting the German V-1 flying bombs, early cruise missiles that had begun to present a new threat to London and its surrounding areas. The V-1 was a formidable adversary in terms of speed, cruising effortlessly at approximately 400 miles per hour at low altitude. To intercept and neutralize these flying bombs, fighter aircraft needed to match or surpass this speed at low levels, where increased air density could considerably reduce aircraft performance. Unfortunately, some of the most advanced fighters of the time, such as the Hawker Tempest and the Spitfire Mark 14, struggled to catch the V-1s, often falling short of the required speeds. Standard fuel tanks on the legendary P-51 Mustangs, when filled with regular fuel, provided only marginal assistance in this regard, lacking the necessary speed margin for reliable interception. However, with the introduction of grade 150 fuel, the story changed fundamentally. The enhanced fuel increased engine power and overall aircraft performance, granting the Mustangs a crucial advantage. Specifically, the new fuel provided the aircraft with enough extra speed margin to close the gap and intercept the fast-moving V-1s reliably. The significance of this breakthrough was demonstrated on June 18 of 1944, when Major Reuben Turner, serving with the 356th Fighter Squadron, achieved a remarkable feat. He destroyed a V-1 flying bomb by deliberately tipping its wing using his P-51's wingtip. This daring maneuver, now known as wingtip tipping, became emblematic of the innovative tactics developed during this campaign. Executing this approach required exceptional skill and precise timing. The pilot needed to drive his fighter to incredible speeds, positioning his wingtip within mere inches of the V-1's surface. Once in the optimal position, the airflow from the fighter's wing would induce a controlled roll, nudging the volatile flying bomb off course into the ground or a safe area. It was a high-risk, high-reward maneuver predicated on outstanding piloting precision. During that period, at least 16 successful interventions employing this technique were documented, all made possible by the improved thrust and speed provided by the new fuel. Starting in June of 1944, with the Allied invasion of Normandy looming, American P-51 fighters equipped with the enhanced fuel began playing a pivotal role in achieving air superiority over the invasion beaches. These high-performance fighters took to the skies on combat air patrols and provided crucial escort to the crucial bombing raids that preceded and supported the landings. Reports from German fighter pilots began to emerge, describing encounters with American Mustangs that overcame their expectations, fighters that performed better and faster than previously believed possible. German Luftwaffe pilots and intelligence officers collected numerous reports detailing how these American fighters appeared to possess powers of acceleration and endurance that seemed almost superhuman. They claimed these aircraft could not only outpace German interceptors with ease but also seemed rooted in unexplained reserves of power and performance. Initially, German military intelligence dismissed these reports as exaggerations, or perhaps false accounts driven by pilot fatigue, misperception, or heightened stress levels. Many of their pilots, exhausted from growing losses, were believed to be misreporting or overestimating the capabilities of these fighters. The German command reasoned that the pilots' accounts of American fighters' superior speed and agility might have been the product of tired minds or battlefield frustration rather than actual technological advantage. Consequently, these initial assessments concluded that the American fighters' extraordinary capabilities were likely propaganda or misperception, an overstatement rooted in the chaos and exhaustion of combat. Yet, as the war continued and more post-battle analyses were conducted, the truth gradually surfaced, but not before subsequent test flights of American fighters. among them the iconic P-51 Mustang, the rugged P-47 Thunderbolt, and the versatile P-38 Lightning, revealed striking differences in performance. In particular, the Mustang stood out, astonishing pilots with its remarkable speed, exceptional climb rate, and formidable ability to operate effectively at high altitudes. These qualities earned the aircraft a reputation as one of the most formidable fighters in the Allied arsenal during World War II. However, what many German pilots and enemy combatants failed to realize at the time was that they were engaging with an aircraft whose impressive capabilities had been significantly enhanced well beyond its original design specifications. The American engineers and mechanics, working tirelessly behind the scenes, had found a way to push the Mustang's performance into uncharted territory, an area that the aircraft's initial blueprints and engineering plans had never intended. Operating under conditions of increased power output, pilots were flying at power settings that the very engineers who designed the aircraft had never conceived or authorized in normal operational circumstances. At the heart of this performance boost was the Merlin engine, a marvel developed by Rolls-Royce and produced under license by the Packard Motor Car Company in the United States. This engine was originally carefully engineered with strict thermal limits, designed to sustain certain maximum temperature thresholds, bearing loads, and detonation margins. Its reliability and durability depended heavily on keeping operating conditions within these carefully calculated boundaries. Yet, when American pilots commenced flying with the new, higher boost pressures, a method to extract more power, the engine's operational parameters were pushed perilously close to their breaking points. Under such extreme operating conditions, the engine's components endured more thermal stress, and the risks of knock or detonation increased dramatically. It was here that fuel chemistry came into play as a critical enabler. The introduction of 150-octane fuel, referred to as Grade 150, revolutionized the way engines could be operated. This fuel variant allowed pilots to run their aircraft engines at much higher boost pressures and power settings without succumbing to the destructive phenomenon of detonation, which previously would have caused catastrophic engine failures. Detonation occurs when fuel-air mixtures ignite prematurely due to excessive heat and pressure, violently damaging engine components. Understanding the science behind this breakthrough involves an appreciation of the intricate interactions between fuel molecules, air, and the extreme heat and pressure within the combustion chamber. The key component making this possible was tetraethyl lead, a chemical additive known for its ability to slow the tendency of fuel to ignite spontaneously. By interfering with the chemical chain reactions that cause knocking, tetraethyl lead increased the anti-knock properties of the fuel significantly. Nevertheless, this chemical ingenuity came with placing some serious trade-offs. Tetraethyl lead, as an additive, was highly toxic, necessitating meticulous handling procedures by ground crews to prevent poisoning and environmental contamination, and it posed health risks if inhaled or absorbed. Additionally, the arsenic-based additive left behind deposits on critical engine parts, spark plugs, valves, and cylinder walls, culminating in increased maintenance demands and more frequent component replacements. Fighter groups equipped with this high-grade fuel quickly adapted their maintenance practices, recognizing that the improved fuel performance was accompanied by heightened wear and tear. Spark plugs tended to foul more rapidly, requiring more frequent replacements. Likewise, cylinder inspections became a routine part of maintenance schedules, and engine overhaul intervals were shortened to prolong operational reliability. Despite these challenges, the enhanced aircraft performance, higher top speeds, better climbability, and improved high-altitude operation was deemed to outweigh the increased logistical burden. From a pilot's perspective, The shift to 150-octane fuel demanded not only technical adjustments but also new operating procedures. Pilots were trained to exploit the higher manifold pressure limits, pushing engines harder when necessary, especially at higher altitudes where the thinner air helped mitigate some risks. At the same time, they had to exercise disciplined management of fuel consumption, understanding that operating at maximum boost consumed fuel at an unprecedented rate. Running engines at the highest boost settings rapidly depleted the aircraft's fuel reserves, especially considering that the Mustang's range had already been stretched thin during long escort missions to targets such as Berlin and back. Thus, effective use of the new fuel's capabilities required meticulous fuel management strategies. Pilots needed to recognize when to throttle back for cruising, conserving fuel, and when to unleash maximum power during tactical combat situations. Historical reports from the summer and autumn months of the year 1944 provide compelling evidence of this transformation. Fighter groups within the 8th Air Force, armed with the improved 150-octane fuel, reported a notable increase in their success rates, reflected in higher victories and lower losses. The enhanced power and agility of the Mustang allowed these pilots to more effectively intercept and combat German fighters that previously had been capable of quick, slashing attacks, then retreating before formations could respond. German fighters, which relied on speed to perform hit-and-run attacks, now found themselves at a disadvantage. Their traditional tactics of rapid assaults followed by swift escapes were less feasible against the 357th Fighter Group, renowned for their missions as part of Operation Frantic, which involved flying supplies and support to Soviet air bases, found themselves engaged in combat with German fighters over Eastern Europe on more than one occasion. One such critical encounter involved Captain Neylan, a skilled pilot flying his trusted P-51D Mustang, affectionately named Hell's Bells, and fueled with a mixture of approximately 150 grade aviation gasoline, an echelon of fuel that promised exceptional performance. During this skirmish, Neylan spotted a Messerschmitt Bf 109, flown by the German pilot known as Schack. The engagement quickly intensified as Neylan, leveraging the speed advantage afforded by his aircraft and the high-performance fuel, rapidly closed the distance to his adversary. With precision and decisive action, he unleashed a burst of gunfire, inflicting damage on the German fighter's cooling system, a vital component that impacted the aircraft's ability to sustain operations but did not cause immediate catastrophic failure. After this fierce exchange, Neylan, aware that his aircraft was now running low on both fuel and ammunition, chose to break off the pursuit. Instead of pressing the attack further, he gave a respectful wave to the German pilot, a gesture of both solidarity and acknowledgement, and turned back to his essential escort duties. Meanwhile, Schack, the German pilot, managed to bring his damaged aircraft in for a belly landing near German lines, a risky but necessary move. Throughout the subsequent decades, Schack would ponder why Neylan had not finished him off, never grasping that Neylan's actions stemmed from a belief that he had merely inflicted damage, not dealt a definitive kill on the German fighter. Many years later, fortune and history would intertwine by reuniting the two pilots in Germany, where they were able to meet face to face. Schack confessed that the performance of the American Mustang had been unlike anything he had encountered before. The incredible acceleration, the rapid closing speeds, and the resilience of Neylan's aircraft during the combat left a profound impression. The way Neylan had closed the distance almost instantly, coupled with the remarkable energy reserves displayed during the fight, exceeded what Schack had known in prior encounters with American fighters. Such encounters had a profound psychological impact on Luftwaffe pilots. Already outnumbered and burdened with the complex task of defending an extensive and increasingly vulnerable homeland, they were now forced to confront American fighters capable of extraordinary speed, maneuverability, and endurance, traits that seemed to have no apparent limit. The once straightforward tactical options for German pilots had become sharply constrained. Their choices had narrowed to just a few, each fraught with peril. One option was to attempt massed attacks, hoping to overwhelm the American escort fighters with overwhelming numbers rather than engaging in one-on-one dogfights. Alternatively, they might choose to avoid combat entirely, preserving their aircraft and pilots for critical missions, though at the risk of losing valuable opportunities and strategic positions. The third option, and perhaps the most daunting, was to engage directly, though experience and previously documented encounters suggested that such a gamble often resulted in the German aircraft being shot down, as American fighters like the Mustang proved to be faster, more agile, and piloted by increasingly confident and assertive American pilots. The grim reality of this familiar pattern was famously acknowledged by Reich Marshal Hermann Göring, the commander-in-chief of the Luftwaffe. Upon witnessing the P-51 Mustang's sweep over Berlin, Göring famously declared that, at that moment, he knew the war was effectively lost. His words vividly captured the strategic dilemma faced by the Luftwaffe. These Mustangs, with their extended range and superior speed, meant that no corner of Germany's vast territory was truly safe from American daylight bombing campaigns. The situation worsened further in mid-1944, when the Germans discovered that the Americans had developed an aviation gasoline of the highest grade, approximately 150 octanes, that vastly surpassed the fuel qualities previously used by German synthetic fuel plants. This discovery came through intelligence obtained from captured drop tanks or wrecked aircraft during raids. German chemists analyzed these samples and quickly confirmed what Luftwaffe pilots had sensed during combat. The Americans' aviation gasoline exhibited exceptional performance characteristics, enabling American fighters to outperform even the most advanced German fuels. There were occasional reports suggesting that, toward the very end of the war, some production batches of C3 fuel, an inferior grade, approached comparable performance levels to the top-tier 150-octane fuel, but these claims were tenuous at best. Production of such high-octane fuel remained limited, and quality inconsistency was a significant problem. Furthermore, heavy Allied bombing raids targeting German synthetic fuel plants, especially those at Leuna and other major facilities during May and June of 1944, caused further disruptions in German fuel production and distribution. By late 1944, fuel shortages became critically acute throughout Germany, forcing the Luftwaffe to ration every drop. Fighter units received priority in allocation, yet even these aircraft had to operate under severe constraints. Training for during the early stages of deployment, pilots assigned to operational units often had significantly less flying experience when compared to their American counterparts, who generally had accumulated several hundred flight hours before stepping into combat situations. This disparity in training was a notable feature of the air campaigns at the time and often influenced operational outcomes and aircraft survivability. In the period spanning from January to May of 1944, the strategic deployment of American bombers was encountering losses at a rate ranging approximately from 3 to 6% per mission. Before the widespread adoption of the advanced aviation fuel known as 150-grade fuel, these losses, though substantial, could be considered within a manageable range, albeit markedly painful when expressed in human and material terms. This period was characterized by ongoing logistical and tactical challenges, and the high loss rates underscored the urgency for technical improvements and operational refinements. Following the introduction of the more potent 150 grade fuel and the achievement of clear air superiority, the losses experienced by American bomber forces witnessed a significant decline. Between June and December of 1944, the loss rate per mission fell to below 2%, demonstrably improving the sustainability of bombing campaigns over occupied Europe. This reduction in losses was not solely due to better fuel. It also reflected enhanced tactical coordination, improved escort fighters, and the strategic advantage gained in controlling the skies. During this same interval, the number of aerial victories claimed by American fighter groups operating across the 8th, 9th, and 15th Air Forces increased markedly. In total, these units reported a combined figure of roughly 4,950 German aircraft shot down in air-to-air combat engagements from late 1943 through May of 1945. A noteworthy aspect of these combat victories was their concentration in the period after June of 1944, subsequent to the critical D-Day landings and the subsequent establishment of Allied footholds in France. It was decidedly after this turning point that German Luftwaffe pilots faced a rapid and systematic erosion of their force, despite entering 1944 with notable experience, especially on the Eastern Front. The relentless attrition inflicted by Allied aerial superiority ultimately led to the decimation of the remaining German fighter force, which had previously been numerically substantial. By D-Day, June 6, 1944, the German Luftwaffe's presence over the Normandy beaches was remarkably diminished. Officially, only a handful of their aircraft appeared during the crucial Allied invasion. While the Luftwaffe still retained thousands of fighters in reserve, they faced severe constraints, most notably a lack of sufficient fuel, a dwindling pool of well-trained pilots, and an inability to operate with tactical flexibility comparable to their adversaries. These shortcomings severely limited their effectiveness in defending occupied France and supporting German operations. An essential component in this decline was the deployment of the new grade of fuel designated as 150 grade. This fuel was characterized by its particular octane rating and combustion properties, which had significant implications for aircraft performance and operational handling procedures. The octane rating of 100 for this fuel indicated a high resistance to engine knocking or detonation, comparable to that of pure iso-octane when engines operated at cruise settings. This property was critical because detonation could cause severe engine damage or failure, especially under accelerated power demands. Furthermore, the fuel's rich mixture performance number of 150 meant it was capable of tolerating 50% more compression than iso-octane under maximum power conditions, an extraordinary benefit for high-performance aircraft engaged in combat and rapid maneuvering. This permitted pilots to cruise and loiter effectively over extensive distances, conserving fuel and maximizing range, before switching to richer mixtures at higher power settings for combat. The confidence in the high-octane properties meant that engines could operate under increased boost pressures without risking detonation, thus providing pilots with greater tactical advantage. Handling of the 150 grade fuel required particular precautions, primarily due to its elevated tetraethyl lead content. Ground crews were mandated to wear protective gear during fueling operations to reduce the risk of poisoning from lead vapors, and any spills had to be promptly cleaned to prevent exposure. Additionally, fuel trucks and storage tanks were meticulously marked and segregated to prevent accidental mixing of different fuel grades, thus ensuring operational safety and engine integrity. Despite these stringent safety precautions, the overall safety record concerning fuel handling remained commendably high, with industrial accidents being relatively rare. The logistical shift to include this new grade of fuel also entailed urgent pilot training initiatives within operational squadrons. Pilots received detailed briefings revealing the unique properties of the 150-grade fuel and instructions on the revised engine operating procedures needed to fully exploit its benefits. These updates included raising manifold pressure limits and confirming when and how to set maximum power configurations safely, thus optimizing aircraft performance without risking engine damage. Remarkably, the aircraft themselves required no fundamental modifications to utilize the new fuel. The engines, fuel systems, and all associated components were already compatible with both grades of fuel. This inherent compatibility represented a significant logistical advantage, simplifying supply chains and operational planning. No extensive refitting or overhaul was necessary in the midst of the tumultuous years of World War II. A crucial element often overlooked was the quintessential role played by premium quality aviation fuel, specifically, the highly refined and specially formulated grade known as 150 grade fuel. This particular type of gasoline, characterized by its distinctive purple dye, became a vital component in enhancing the performance of Allied aircraft, especially fighters like the P-51 Mustang. The meticulous process that ensured the cleanliness, purity, and catalytic quality of this fuel involved rigorous quality control testing, safeguarding the supply chain from contamination, and meticulously transporting it across vast distances, ultimately delivering it to dozens of airfields scattered throughout Europe. Once there, it was stored in highly secure facilities designed to prevent any contamination or sabotage, and then distributed with precision to support the relentless aerial campaign against the Axis powers. By the year of 1944, American industrial capacity seemed nothing short of miraculous. The United States had ramped up wartime production to levels that conveyed an almost unbelievable scale of manufacturing efficiency and determination. Factories hummed day and night, churning out aircraft at astonishing rates. Thousands of bombers and tens of thousands of fighter planes rolled off assembly lines, symbolizing a relentless industrial engine of war. American shipyards, often working around the clock, launched Liberty ships at speeds that outpaced the rate at which German U-boats could sink them, maintaining a steady flow of support vessels across the Atlantic. Meanwhile, oil refineries operated at full throttle, producing aviation-grade gasoline in quantities that surpassed Germany's entire fuel output across all grades, an industrial achievement rooted in decades of technological development, vast natural resources, and a system designed for maximum efficiency. The United States' unparalleled industrial output alone would not have been sufficient without a protected homeland and a resilient workforce. A significant portion of this workforce consisted of millions of women who stepped into factories in unprecedented numbers to support the war effort. Their contributions allowed the production capacity necessary to meet the rigorous demands of wartime logistics. On the other side of the Atlantic, the Royal Air Force, RAF, also capitalized on high-octane fuels, particularly the 150 grade, using it extensively in their fighter operations across Europe. The British squadrons, flying some of the most iconic aircraft such as the Spitfire Mark 14, Tempest V, and Mustang Mark III and IV, received prioritized allocation of the new, superior fuel source. RAF pilots quickly reported experiencing performance enhancements similar to those documented among their American counterparts, confirming that the Tempest V, already reputed as one of the swiftest piston engine fighters in service, became even more formidable with the adoption of the high-grade fuel. The improvements in aircraft performance translated directly into increased success and lethality, particularly evident in the Tempest's exceptional record against the V-1 flying bombs. During the summer months of June through September of 1944, the Tempest-equipped units credited with shooting down a staggering 638 V-1 flying bombs, an achievement that significantly contributed to defending Britain from the terrifying wave of these early cruise missile threats. An astonishing 305 of these kills were claimed by just the 3rd Squadron alone. Notably, Squadron leader Joseph Bry, one of the most successful aces against the V-1s, achieved an impressive 59 confirmed kills. Other notable aces included Belgian squadron leader Remy van Lierde, who destroyed 44 V-1s, and wing commander Roland Bymont, who claimed 31. The next most effective interceptors included the versatile Mosquito, which tallied 623 victories, the Spitfire Mark 14 with 303, and the Mustang with a total of 232 successful kills. This consistent performance boost underscored the vital margin of superiority the 150 grade fuel conferred on Allied aircraft, demonstrating its added value in every operational role. The combat effectiveness of this exceptional gasoline was repeatedly proven through rigorous tests and real-world engagements throughout the end of 1944 and into early 1945. Durably bolstered, fighter groups that incorporated the new, high-quality fuel reported having increased victory claims and significantly lowered their losses, bolstering morale and confidence among Allied pilots. By the month of March in 1945, nearly every operational P-51 Mustang unit had transitioned to using this high-grade fuel, reflecting its perceived importance. Throughout the final months of the European conflict, combat reports cumulatively painted a clear picture of a vastly imbalanced aerial battlefield. The results were overwhelmingly one-sided. German fighters rarely mounted effective defenses or represented a genuine threat to Allied formations. When Germany's Luftwaffe did engage, they often suffered heavy losses that were devastating, given their diminishing numbers and the dwindling expertise of their remaining pilots. By the time April of 1945 arrived, missions flown over German territory frequently encountered no aerial opposition at all, highlighting the collapse of German air power. This decline was driven by attrition, expected losses, fuel shortages that hindered operations, and a systematic eradication of the skies over Europe had become a battlefield not merely shaped by raw aircraft numbers or pilot bravery, but fundamentally driven by the quality and availability of the fuel that powered these machines. The swift, agile fighters flown by the Allied forces possessed a remarkable tactical advantage, something that gave them the critical flexibility to decide when to engage aggressively and when to withdraw strategically. This advantage stemmed from an intricate combination of cutting-edge aircraft design, superior fuel supplies, and a robust logistical framework that kept their air forces operational under conditions that would cripple their adversaries. As the war progressed into late 1944 and early 1945, a significant divergence appeared in the operational realities experienced by German and Allied pilots. Allied fighters, especially those like the iconic P-51 Mustang and the Spitfire, could complete multiple sorties in a single day. Their endurance was less constrained by fatigue or mechanical wear and tear, thanks largely to abundant fuel resources and a well-established maintenance infrastructure. These aircraft could afford to push their engines hard during combat, confident that they had sufficient reserves left for the return flight and subsequent missions. Their crews enjoyed a strategic edge derived from this operational flexibility, a luxury that enabled aggressive tactics, continuous patrols, and persistent altitude control over enemy territory. On the other hand, Deutsche Luftwaffe fighters often faced a dire supply situation. They frequently sat grounded at airfields due to a shortage of fuel, which was a consequence of a war economy increasingly stretched thin. When fuel allocations were allocated for operations, pilots were required to adhere to strict conservation measures designed to stretch every drop of fuel as far as possible. These restrictions significantly limited their combat effectiveness. German pilots had to choose their moments judiciously and often could not maintain a high-energy pace throughout a sortie. The reality was stark. Breaking off a fight was less a strategic choice and more a necessity. When fuel supplies ran dangerously low, pilots had little option but to disengage, not necessarily because they were losing the fight but because they lacked the fuel to stay in it. This scarcity revealed itself in the mindset of the Luftwaffe pilots. Each sortie could be potentially their last, whether because they might encounter enemy fighters that could shoot them down or because they simply might run out of fuel before returning to base. This situation starkly contrasted with the confidence of Allied pilots, whose aircraft, fuel supplies, and logistical support appeared virtually unlimited. They took to the skies assured in the knowledge that their aircraft boasted superior speed, agility, and endurance, underpinned by an extensive industrial effort aimed at sustaining their flying fleets. The result was a psychological and tactical edge, an environment in which the Allies could afford to be more aggressive, more assertive, and ultimately more successful in the air. The pivotal importance of pneumovating fuel, specifically the kind that met rigorous quality standards, became apparent during this period of intense aerial combat. The story of this particular grade of gasoline underscores the broader narrative of industrial warfare, where victory was not merely about producing more aircraft but also about manufacturing better, more powerful ones. It wasn't just enough to have sufficient fuel. What mattered was the availability of only the highest quality, most efficient fuel that would maximize engine performance and aircraft capabilities. This superior fuel facilitated rapid acceleration, sustained high speeds, and longer flight durations that often decided aerial engagements in favor of the Allies. Behind the scenes, a complex web of scientific research, chemical engineering, and industrial production fueled this advantage. American and British chemists, engineers, and refineries, as outsiders to the front lines of combat, worked tirelessly in laboratories, test stands, and processing plants. Their efforts focused on refining crude oil into a specialized type of fuel that met exacting standards, often detailed in performance numbers and manifold pressure readings, that determined how effectively aircraft engines performed at altitude or during high-speed maneuvers. These scientists never faced the dangers of enemy fire firsthand, yet their meticulous work was instrumental in shaping the balance of power in the skies. Every time a P-51 Mustang pilot thrust his throttle forward, experiencing the surge of power driven by this advanced fuel chemistry, enabling him to outpace German fighters or escort bombers through heavily contested airspace, he was unknowingly benefiting from a pinnacle of chemical engineering. This is the reality. The transformation of crude oil into a refined, high-octane fuel capable of making performance the norm rather than the exception. Such manufacturing infrastructure and scientific prowess allowed the Allies' fighters to consistently outshine their German counterparts, who had originally believed that aircraft would perform predictably based on their design parameters and the standard fuels available to them. However, what Germany encountered by the final years of the war was starkly different. They faced fighters that often exceeded the performance limits they had anticipated, sustained by a fuel production capacity so enormous and sophisticated that it became an insurmountable industrial challenge for Germany's war economy to counter. By the time spring arrived in 1945, the industrial disparity encompassing fuel production, technological innovation, and logistical support had become a decisive factor, tipping the balance of aerial dominance firmly in favor of as the Allied forces advanced relentlessly across Germany from both east and west. The once formidable Luftwaffe had gradually disintegrated into a fragmented and ineffective fighting force. For all practical purposes, it had ceased to exist as a cohesive and capable military organization, capable of mounting significant against-the-odds sorties or challenging the supremacy of Allied air power. What remained were only a handful of units that continued to take to the skies, often barely maintained with enough fuel for a single mission, knowing full well that their chances of a successful sortie were slim at best. The advent of jet fighters, exemplified by the introduction of aircraft such as the Messerschmitt Me 262, marked a revolutionary leap forward in aviation technology. These aircraft showcased the rapid advancements in aeronautical engineering, offering unprecedented speed and performance compared to propeller-driven fighters. However, despite the impressive nature of these innovations, they arrived too late in the war and in insubstantial numbers to alter the overarching outcome. The Luftwaffe's jet push was hampered not only by significant shortages of fuel, especially high-octane fuel necessary for maximum performance, but also by the lack of experienced pilots. Many of the Luftwaffe's skilled aviators had been systematically lost in combat, leaving behind a cadre of relatively inexperienced men at the controls of cutting-edge aircraft with limited operational capabilities. The tragic and ultimately decisive tally of air combat and ground destruction underscores the cumulative weight of Allied dominance on multiple fronts. Throughout the conflict, American fighter groups, employing aircraft like the P-51 Mustang, launched hundreds of thousands of sorties across various theaters of war. These aggressive operations resulted in claimed totals nearing 5,000 enemy aircraft shot down in aerial combat, complemented by the destruction of well over 4,000 aircraft on German airfields and ground installations, targets that represented vital components of the Nazi war machine. However, these figures tell a story that extends beyond mere numbers of aircraft destroyed. Each claimed victory also represented the loss of individual pilots, fathers, sons, and skilled aviators, whose experience and expertise vanished in the chaos of combat. The destruction of German aircraft factories and manufacturing facilities thwarted the production of replacements, meaning each destroyed airplane was not simply a piece of machinery but also a blow to the country's industrial capacity, which could not be quickly or easily replenished before the tides of war shifted irreversibly. While a shortage of fuel, specifically around 150-octane gasoline, was not solely responsible for this downfall, it played an undeniably crucial role. This scarcity undermined the Germans' ability to maintain and effectively operate their aircraft, tipping the scales toward Allied supremacy. The margin of superiority, almost imperceptible to the untrained eye, represented the pivotal difference that separated a fierce, uncertain engagement from a decisive victory. The American P-51 Mustang, which could reach speeds of about 448 miles per hour when properly boosted, embodied far more than raw velocity. Its advanced design reflected the sophistication of Allied industrial capacity and technological innovation, demonstrating superiority that German planners had not anticipated. This increased performance was not merely a matter of pushing a plane to higher speeds but was deeply rooted in groundbreaking developments in fuel composition and engine design, elements that changed the very nature of aerial combat. Unbeknownst to many at the start of the conflict, American teams of fuel chemists and petroleum engineers, working in laboratories far removed from the chaos of the battlefield, had crafted a weapon just as potent as any gun or explosive device: high-octane aviation fuel. This specialized liquid, famously dyed purple for easy identification, vastly enhanced the power, speed, and agility of American fighters like the Mustang, turning them into nearly unstoppable fixtures of the European skies in 1945. Its impact was comparable to strategic advantages gained through superior tactics or rigorous training, yet it was rooted in the seemingly mundane realm of chemistry and engineering. This fuel revolution was driven by advances in refining processes that boosted the compression ratios of piston engines and improved the anti-knock properties of aromatic hydrocarbons, chemical compounds essential in producing high-octane fuels. These technical improvements allowed aircraft to operate at higher manifold pressures and more optimal performance levels, translating into increased airspeed, better climb rates, and superior overall efficiency. In a war where milliseconds could decide the fate of a mission and the future of a continent, such minute enhancements in fuel quality had enormous strategic implications. The aircraft that streaked over Berlin in early 1944 were already remarkable machines, fighter aircraft of impressive design and capability, but by early 1945, the same aircraft were powered by refined fuels that unlocked their full potential. Step by step, the difference in performance was quantified through measures such as octane ratings, manifold pressure readings, and airspeed indicators. Metrics that reflected how well engineered the aircraft and their power sources truly were. These performance variances, harmless-looking numbers to the untrained eye, were, in fact, the invisible yet decisive factors that played a vital role in determining who would ultimately gain control of the skies over Europe. Thus, the outcome of